Hello everyone, welcome back to PC301 workshop, and we are here with the final session of the day. And we have with us Professor Daniel Lokshtanov from University of California, Santa Barbara, and he'll be talking on exact algorithms via monotone local search. Thank you so much for joining us, Daniel. Over to you now.
Thanks for the invitation to speak. So can you guys hear me well?
Yes.
Yeah, okay. This is based on now not that recent, 2016-ish joint work with Fedor, Serge, and Socket. But also for about half of the talk, I'm going to be talking about much older work on satisfiability by other people, because that in many ways led up to our work. And given that I now have almost a full hour to speak, and the second part is pretty quick to cover, I think some of the back history and also the techniques from there are useful to know. So this is what the talk is about, and this is, well, you've been learning now about how to design parameterized algorithms, and in particular fast parameterized algorithms. And it's very natural to ask yourself, well, can we turn these fast parameterized algorithms into algorithms that are good or work sort of faster than brute force on all instances? So in particular, if you now change the parameter to input size or whatever is like the classic way of measuring the running time for algorithms for your problem, the question is, well, if you have a fast parameterized algorithm for your problem, can you then get a fast exact algorithm? So for example, if you have a 3 to the k algorithm, does that mean you can get a 1.5 to the n algorithm, or say beat 2 to the n? Or for every value of 3, what is the lowest value of 1.5 that you could get? And of course, the very first thing you should ask yourself in a situation like that is what is k, right? Because k can be the solution size, it can be the solution quality, k can be the size of a set, or it could also just be something like tree width, which is harder to capture easily as a more general concept of what the parameter is for a number of problems. So we're going to restrict ourselves to the easy case of subset problems, where there is some universe of size m, and we are looking for some hidden subset of size k. So a little bit more formally, there is a universe of size m, and there is an implicit family of subsets of the universe. What does it mean that it's an implicit family? You can think of it as an oracle, where I ask you, is this set in the family? And the oracle answers yes or no. Is this set in the family? The oracle answers yes or no. And that's all you know about it. And what you're interested in knowing is this set in the family or not? Like, or is the set in the family, is the family non-empty or not? Yeah. So here is a simple example. Satisfiability. So suppose I give you as input a formula over a set of variables, then the universe can be the set of variables, and we can set the family F to be the family of all satisfying assignments to the formula. Now, I lied a little bit, right? Like, I'm talking about the family of all satisfying assignments, where the family has to be of sets over universe. So we need to encode the set of satisfying assignments as a family of sets over the universe. So if we can encode a single assignment as a set, it could be the set of variables that are set to true, right? So if x1 through x10 are set to true and the rest are set to false, we encode that as the set x1 through x10. Okay, so now the family contains all of the sets that correspond to assignments that satisfy the formula. And now looking for a satisfying assignment corresponds to answering whether the family is non-empty or not. Okay, another problem that you probably saw during this course, feedback vertex set, I give you a graph G, and you're interested in knowing G and integer K, and I ask you, does there exist a set of vertices of size at most K, so that removing it leads to an acyclic graph? Okay, well, how do we encode this as a subset problem? Well, the universe is the set of vertices, and the family is the set of all vertex sets of size at most K that are feedback vertex sets. Okay. Finally, you can also encode some funky things like 3 coloring, like vertex subset problems, as in looking for independent subsets so that removing them leaves the bipartite graph, right? So now notice that F is non-empty if and only if the graph G has a proper 3 coloring. Okay, so any questions to this? Let's see.
So Daniel, the graph G for the third example, the graph G is not known as in the edge relationship. That remains implicit always in the back.
Yes. So for the purposes of this talk, you can think of the edge relationship remains implicit. But really, when I say an implicit family of subsets, you can think of it like you're given some object that defines a family of subsets over a universe. So for example, I will give you the graph G and integer K. That the graph G and integer K now defines the set of all feedback vertex sets of size K of that graph.
Right.
Yeah. So you can switch between the more formal statement where you don't have access to the graph at all, which our algorithms won't need, right? Or a setting where you have access to the input instance, but really what you care about is that the input instance is defining some family of sets over a universe.
Right.
And all you're interested in knowing is this family empty or not?
Right. Okay. Thank you.
Okay. So what are we interested in? Well, we are asking. So one is. What is the brute force? The brute force would just be now, if you have Oracle access, try all sets.
Hello?
Yes?
Sorry, there's a question in the chat. Is 4 coloring analogously representable in this framework?
Yes, except that now so yes, in the sense that you can say that does there exist an independent set so that removing it leaves a 3 colorable graph, but checking whether a graph is 3 colorable isn't a polynomial time operation. So now your Oracle, you cannot evaluate the Oracle in polynomial time, right? So I guess some of our theorems will survive in this setting, and they're phrased in a way in which they will survive if someone implements the Oracle efficiently, but we don't believe that the Oracle can be implemented efficiently.
Okay, thanks.
Yeah. Okay. So what is the brute force for subset problems? Well, you just try all subsets, check whether they're in the family or not. If you find a set, you're done. That takes 2 to the n time. So then what you're interested in is C to the n algorithms for some constant C less than 2, right? Like 1.99 to the n, but if you're really lucky, you can get 1.001 to the n. Okay, now what about parameterized algorithms? The most natural parameterization would be K, the size of the solution, right? So find a solution of size at most K, if it exists, in time C to the K polyon for smallest possible C. Okay, and now the question is, suppose you have a 10 to the K algorithm for the parameterized problem, does that imply that you can beat brute force for the exact one? Okay, the answer is that in this talk, yes, surprisingly often. For most subset problems, for most reasonable subset problems, the answer is yes. So first, we're going to go to a particular subset problem where the answer is not just yes, it's a resounding yes. In fact, for a very long time, the fastest known algorithms for satisfiability were based on this kind of technique. Okay, so what is DSAT? Input is a formula phi with n variables in DCNF. So this is D conjunctive normal form. What does it mean? It means that your formula consists of clauses. It consists of an and of clauses, and a clause is just an or of literals, where a literal is either a variable or its negation. So on your screen now, you see a formula in 3CNF over the variables x, y, and z. Now, of course, if you set the variable x to true, then its negation is set to false. A clause is satisfied if at least one of its literals is set to true. And the formula is satisfied by an assignment if all of the clauses are satisfied by the assignment. And finally, a formula is satisfiable if there exists at least one satisfying assignment for the formula. So here, setting all of them to true is a satisfying assignment. You can check that in the first clause, x is true. In the second one, in the second clause, x is true, and in the last one, for example, z is true. So this is a satisfying assignment. Setting all of them to false is also a satisfying assignment, because each clause contains a false literal. And finally, for example, setting x to false, y to false, and z to true is not a satisfying assignment because the first clause would not be satisfied. Okay, so what do we know about algorithms for DSAT? Well, it is a subset problem, right? The set of satisfying assignments to a DCNF is an implicit family, and we can just try all assignments, which corresponds to trying all subsets. So getting a 2 to the n algorithm is easy. And you might have seen strong ETH by now. And strong ETH posits that you cannot have a 1.9999999 to the m algorithm where the number of nines is independent of the d. So there is this strong exponential time hypothesis, which is just a conjecture. We don't know whether it's true or not, but it would be a major, major breakthrough if someone managed to get an algorithm for DSAT with running time 1.999 to the n, where the number of nines is independent of d. So you get 1.999 to the n algorithm for 10 sat, for 100 sat, and for 100,000 sat, for every value of 100,000. So any questions to what strong ETH means?
So basically the point is that it's not, so the D should have some, it's strongly believed that D should have some role to play in that best time complexity we get for DSAT, right? That's the thing.
Yes, exactly. So the sweet spot, the place where it's possible and there exist algorithms, and the ones that we're going to see right now, is algorithms with running times on the form 2 minus some function of D to the power n. And in particular, 3-sat, right? So the formula you see on the screen now is an example of a 3-sat formula, because every clause has size at most 3. 3-sat is already NP complete. And so for the purposes of this talk, you can just as well think of D as being equal to 3. And now you ask yourself, well, can I get the 1.5 to the n algorithm for 3-sat? But with the additional knowledge that, well, if you wanted an algorithm for 100,000 sat, then the running time of that algorithm better be pretty close to 2 to the n. Yeah. Okay. So how are we going to arrive at a fast algorithm for 3-sat? Well, we're going to look at the local search version of satisfiability. So again, just as before, here input is a formula with n variables, and it should be in DCNF, so just as the previous problem. But now I'll also give you an assignment to the formula, and I'll give you an integer k, and I'll ask you, where k is now again the parameter, and I ask you, does there exist a satisfying assignment that has Hamming distance at most k from the given assignment alpha? So I give you an assignment, alpha, which, let's say, you can think of it as a hint of, well, I hope the satisfying assignment to the formula is close to alpha. Yeah. And then now your job is to find that satisfying assignment. And what is close? Well, within Hamming distance k, that means within k variable flips. You can pick at most k variables and flip them from what alpha tells them to be, from true to false or false to true, and you want to find a satisfying assignment to the formula phi. Now, notice that SAT has this nice property that this problem is actually very easily reducible to the problem where you want to find just where you're, instead of given phi and alpha, I could just give you phi and ask you, does there exist a satisfying assignment of Hamming weight at most k? So a satisfying assignment where at most k variables are set to true. The reason for that is that you can go through alpha, and every time a variable is set to true by alpha, you can go through the formula and then change all of the occurrences of the variable that are true, or change all true literals of that variable to false, and all false literals to true. And then in alpha, you change the assignment to that variable from true to false. Yeah, and you can check that that still doesn't change the answer, whether there exists satisfying assignment within Hamming distance at most k. From alpha, that doesn't change. So what does that mean? It means that without loss of generality, alpha is the all false assignment. And if alpha is the all false assignment, then this question of local search actually reduces to the standard parameterized question, does there exist a solution of size at most k? This isn't something that we're going to be using. We're going to be talking about local search in the rest, but just so that you get a feeling of why does this sort of, like, why does this fit into the way of thinking of the entire talk? Does finding solutions of size at most k lead to faster exact algorithms? Well, for SAT, local search and finding a solution of size k is actually the same thing. Any questions to this? Let's see.
Yeah, so I have one question. So here, so this local search algorithm for SAT problem. So generally, it's a well-known algorithm. I don't remember the name, but the k is n/2, I guess, in that algorithm.
The k is n/2.
Yeah. Yes.
So when you set k to n/2, then you can always search. You can search from the all true and all false and get whatever is the best possible. So for k equals, so for 3 SAT, this will give you something that is better than 2 to the n. But for higher values, you're going to run in trouble. But we're going to see an algorithm called Schoenig's algorithm where k isn't quite n/2. And so that's actually what I'm going to be talking about in like 10 minutes or so.
Yeah, so my question was, so here k is somewhat so because it's working for some parameter which is a function of n, that is why it is working for k. Will it be for other problems also?
So if you think of, I mean, so the interesting situation is like this, right? So suppose you have a really fast parameterized algorithm, right? Suppose I have a parameterized algorithm with running time 1.5 to the k, and you know that k is at most n. That sort of cheaply gives you a 1.5 to the n algorithm. But you want to extract more than that, because suppose I have 100 to the k algorithm. 100 to the k algorithm doesn't seem to give you anything to get faster than a 2 to the n algorithm.
Okay. Thank you.
let's see. So there is now a question. Alpha is a satisfying assignment? No, alpha is just an assignment. So I give you a formula phi, and an assignment, and I ask you, does there exist a satisfying assignment close to alpha? Yeah. Okay. Okay, I'll continue. All right. So here's a simple d to the k algorithm for local search for SAT. Now that we're far enough into a parameterized algorithm school, I can sketch this one really quickly. Start with alpha, right? So you just start with the assignment, and then you ask yourself, well, either this assignment is already a satisfying assignment, in which case you found a satisfying assignment of Hamming distance 0 from alpha. You output it, yes, you're very happy, right? Otherwise, alpha isn't a satisfying assignment, which means that there exists an unsatisfied clause, right? So what does it mean that a clause is not satisfied by alpha? It just means that all literals in that clause are false. Well, then you know that in any satisfying assignment, one of those literals should be flipped, should be set to the opposite of what they are now. So then you can just guess which one, you can guess which one it is to change, right? Which we can just do by branch in d ways. So you have a recursive algorithm that goes over all of the literals, and it makes d recursive calls, where in each one of the recursive calls, it flipped the corresponding literal to the opposite of what it is in alpha right now. And the key observation in the analysis is that in at least one branch, you change the literal from what it is now, which is different from what it is in the satisfying assignment, to what it is in the satisfying assignment. Because you know that you flipped one literal from the incorrect value to a correct value. And that means that in one of the branches, the Hamming distance to a fixed unknown satisfying assignment decreased by 1. Which means that now, that means that you can run your algorithm recursively with budget k, the budget Hamming distance, 1 less than it was before. Which means that you're getting the recurrence t of k is at most d times t of k minus 1, which of course solves to d to the solves to d to the k. Okay. So any questions to this? So this is a branching algorithm. It's a little, it's a little bit trickier than the first branching algorithm you saw, but other than that, it's just okay. As long as something is broken, branch on the different ways of fixing it. Okay, so we have a local search algorithm with running time d to the k, right? So for 3SAT, it's a 3 to the k algorithm. And now I'm wondering, well, can I turn this 3 to the k algorithm for local search into a better than 2 to the n algorithm into a better than 2 to the n algorithm for 3SAT. And here, there was precisely a suggestion, let's set k equals to n over 2. And now you can run local search from the all true assignment and from the all false assignment. So you just run local search twice, right? Which means that you'll end up with an algorithm with running time 3 to the power n over 2, right? So square root of 3 to the power n, which is something like 1.73 or something like that to the n, right? But say for DSAT, where d is equal to 5, where you would have a 5 to the k algorithm, this trick wouldn't give you anything. So the trick that was mentioned 2 slides ago in a comment was, well, what if we set k equals to n over 2? It actually does give you something meaningful for 3SAT, but it doesn't give you anything meaningful for 4SAT and onwards. Okay, so we now have this local search algorithm. Can we use it in order to get an exact algorithm? I propose the following algorithm. So given as input the formula in n, let's cleverly pick k. So I'm going to set k to be some function of n, and I'm not going to tell you precisely which function yet. And then I'm going to pick an assignment at random, and then I'm going to run the local search algorithm from alpha with distance k. Yeah. And that's the entire algorithm. Now notice that the running time of this algorithm is d to the k. Right? And of course, if I find a satisfying assignment, then it is satisfying. Great. But my success probability isn't polynomial, right? It's not 1 over Polian or a constant. The success probability is the probability of when I pick a random assignment, that random assignment is within distance at most k of a satisfying assignment. Now, notice that as I increase k, I increase the running time of the local search algorithm, but I also increase my success probability. If I picked k equal to n, then my success probability would be equal to 1. Okay, my actual running time. So I have to, if I select k to be much smaller than n, I'm going to have a much smaller success probability. And in order to boost the success probability, I should just repeat the algorithm many times. Well, how many times should I repeat it? 1 over success probability in order to make it constant. Yes. So the actual running time of a randomized algorithm like this would be its running time divided by its success probability, so d to the k divided by p. Okay. So now the question is, what is the probability that a random assignment is within distance at most k of a satisfying assignment? Well, it's a fraction. Now, what is the denominator of this fraction? Well, the total number of assignments, right? Like the probability is of something good happens is the number of ways to do the good thing divided by the total number of things. So we're picking from the set of all assignments. There's 2 to the n of them. And how many good things are there? How many assignments are there within distance at most k from alpha? Well, you start with alpha and you choose the k positions to flip. So that will give you n choose k. Right? It's actually the sum of n choose I for every I goes from 0 to k, but it's more or less equal. It's less than, it's greater to than n choose k, and it's not much greater. Okay, so if this is our success probability, remember the running time is the running time of the algorithm divided by the success probability. So this ends up being 2 to the n divided by n choose k times d to the k. Now this running time depends on k. And how should we pick k? Well, we should pick k so that the running time gets minimized. So let's pick k so that this expression becomes as small as possible. Right? Notice that this expression doesn't depend on the formula at all, right? I can just compute what it is for every value of k between 0 and n without having to run the algorithm. And I'll know which k I should be picking in order to minimize the running time of the algorithm. Okay, so let's figure out what does this expression evaluate to. I don't really have time to do that properly, but I have a slide just to show you that the calculation isn't all that long. You do a little bit of simplification and you realize that this expression simplifies to 2 minus 2 over d plus 1 to the power n. So if you plug in 3 here, if you plug in, if you plug in 3, then you get 2 minus 2 over 4 to the power n. So that is 1.5 to the power n. If you plug in d equal to 9, right? So 9 sat, you get 2 minus 2 over 10 to the n. So that would be 1.8 to the n, right? Yeah. So 9 sat, you actually get a pretty fast, like 1.8 to the n algorithm, which at least I find pretty surprising. Now here is an interesting thing about our final analysis, and this is that a d to the k algorithm for the local search problem implies a 2 minus d plus 1 to the n algorithm for the problem. And this second part, like not the local search algorithm itself for dsat, but the second part of where you picked a random subset and you ran local search from it, didn't depend at all on the fact that we were working with satisfiability. Like this algorithm and analysis works for absolutely any subset problem. If you have a d to the k algorithm for local search, so finding a solution at distance at most k from a given solution, where distance is Hamming distance, right? So you take an element in the set and you move it out of the set, or you take an element that is not in the set and you add it to the set, right? If you have an algorithm with running time d to the k for the parameterized local search for your problem, you automatically get the fast exact algorithm. And notice that this beats 2 to the n for every value of d. That's important. Another interesting question is, can we get a faster local search algorithm for dsat? So if I just ask you, well, we have a d plus 1, or a d to the k algorithm for local search. Can we beat that? So let me briefly outline an algorithm that is a little bit faster than d to the power k for local search. One of the interesting, and this is precisely what's called Schoenig's algorithm. So Schoenig gave an algorithm for dsat, so for 3 sat running in time 2 to the k. So for 3 sat local search running in time 2 to the k. In general, for dsat local search running in time d minus 1 to the k. Now, it's not precisely for the local search problem. It is for the permissive local search problem. So in the local search problem, I give you in the normal local search problem, I give you a formula and a hint. So I give you an assignment alpha and an integer k, and I ask you, does there exist a satisfying assignment that is within distance k to alpha? So even though the formula phi could be satisfiable, it could be that the satisfying assignment is outside of the ball around alpha, in which case the local search algorithm should answer no, right? I mean, perhaps the formula is satisfiable, but there isn't a satisfying assignment close to alpha. But from the perspective of using the local search algorithm for an exact algorithm, this is not behavior that we really need, in the sense that we don't need to say that if there doesn't exist a satisfying assignment within distance k from alpha, but there is one for the formula, you could say yes, you could say no, and which one you say doesn't really matter. So permissive local search goes like this. If there exists a satisfying assignment close to alpha, so within distance k, you should say yes. And secondly, if you say yes, you better output a satisfying assignment. But that satisfying assignment doesn't have to be close to alpha. Okay, so that's what we mean by permissive local search.
And what happens if there exists a false assignment which is outside that k distance ball? Then I can say anything.
You can say yes, you can say no. But if you say yes, you better output a satisfying assignment. In permissive local search, there is only a restriction on what you should say if there exists a satisfying assignment that is close to alpha. In that case, you have to output some satisfying assignment.
Okay, but even then, how is this used? Doesn't this have the same problem that the normal local search would have? Because it's saying nothing outside the ball, right? Even if one assignment does exist.
Well, no, it's not a so it's not a problem, right? What you're saying is you're running, okay. In our context, all we're trying to do is to figure out, does the formula have a satisfying assignment?
Right.
Yes. What are we trying to do? We're going to pick a random assignment and ask, does there exist a satisfying assignment close to this assignment?
Yes.
Yes?
Yes.
Now, instead, we're going to ask the following question. Well, if there exists a satisfying assignment close to this assignment, then give me some satisfying assignment to the formula. And if it doesn't exist, then you can say yes. I mean, then you can, and if it doesn't exist a satisfying assignment, then you should either say no, or you should give me a satisfying assignment to something outside the ball. Yeah, I mean, the important thing is that whenever you output an assignment, that assignment is satisfying. You don't care whether it's inside the ball or not.
Oh, yeah, fine.
Yeah, so you can think about it as I have a problem, so I formula, and you want, and the solution to the problem is a satisfying assignment. And I can give you a hint, and that hint is either useful or not useful. Yeah, and if the problem has a solution and the hint is useful for the solution, then you should find a solution.
Okay.
Okay?
Yeah.
As a corollary, he gets an algorithm with running time 2 minus 2 over d for dsat. Okay? Which is, of course, slightly better. So for 3 sat, right, this ends up being 2 minus 2/3. So this is a 1.333 to the n algorithm for 3 sat, which is incredibly fast. Okay, so Schoening's algorithm looks a lot like our branching algorithm, but instead it's a random walk where you start with of alpha instead. So you start with, let's say, beta equal to the assignment alpha, and then you proceed in 3n steps to do the following. Schoening's algorithm is randomized, yes. It has been de-randomized, but I'm not going to talk about that today. Okay, so this is a randomized algorithm. And what it's going to do is that as long as there is some clause that is unsatisfied by beta, so by the assignment we currently look at, we pick up a random literal in C. So you see that here is your randomness, and you flip that literal in beta. And then you just keep doing that, and you keep checking, well, do I have a satisfying assignment? If not, pick up an unsatisfied clause, pick up a random literal in that clause, flip that literal. And that's the entire algorithm. Now, of course, just as before, this algorithm always runs in polynomial time because you just do something in 3n time steps. Now, if it outputs an assignment, it is a satisfying assignment. Now, notice that this assignment is a satisfying assignment, but it's not necessarily close to alpha, right? Because we start out with alpha, but we proceed in 3n steps. So it could be that we have, by the time we output a satisfying assignment, we've actually moved pretty far from alpha. Yeah. And the actual runtime of the algorithm is 1 over the success probability. So in order to get constant success probability for this algorithm, I need to repeat it 1 over its success probability. And then the number of repetitions is really what dominates the running time. So in order to figure out what the running time is, I have to analyze the success probability, and I have to prove that the success probability is actually upper bounded by 1 over d minus 1 to the power k for dsat. Okay, so here is an analysis of Schoening's algorithm. So let's fix some unknown satisfying assignment. And let R, which initially starts out at most k, be the distance from beta, your current assignment, to the fixed satisfying one. Now, we know that in each step, we decrease the distance from beta to the satisfying assignment if we flip the correct literal in the clause, because we know that we picked up a clause that was unsatisfied. The satisfying assignment has to satisfy this clause. So when we flip a literal, I mean, if we flip the literal that satisfies the clause in the satisfying assignment, then we move towards the satisfying assignment. So we know that in this clause, there is at least one correct literal to flip, and there are d literals. So with probability at least 1 over d, we decrease the distance from our satisfying assignment to, no, from our assignment to the unknown satisfying assignment. And of course, if we do not decrease it, then we increase it, because then we are flipping. Then we're flipping a variable which is set to the same as the satisfying assignment to something that is set to different. So, but of course, we never increase the distance by more than 1, right? Because we only jump 1 at a time. Okay, so in particular, so now what's going on is that in every step, the distance either increases by 1 with probability 1 over d, or either decreases by 1 with probability 1 over d, or it increases by 1 with probability 1 minus 1 over d. So really what's going on is this sort of random walk where you treat the distance as a position on the integers, where you start at k, and in every step you either decrease the distance by 1 or you increase the distance by 1. Yes. So the probability that the algorithm actually finds a satisfying assignment is lower bounded by the probability that if I take a random walk on the integers that moves down with probability 1 over d and up with probability 1 minus 1 over d, the probability that such a random walk will reach 0 in at most 3 n steps. So what does this look like? Well, it looks like this line. You go down with probability 1 over d, up with probability d minus 1 over d, and you start at position k. And now you're interested in what is the probability that you reach 0 in at most 3 n steps. And here I'm going to cheat. And instead of analyzing this probability, I'll analyze the probability that starting at position k, you're going to reach 0 eventually. And here is, so this is a crazy thing, right? Like I'm saying, suppose you start at position k and you're doing this random walk on the integers. And in every step, you either move up or down. If I run the random walk forever, of course, you're going to eventually reach 0 because, I mean, you're going to fluctuate more and more. So eventually, of course, you're going to reach 0. Well, that is not true because the walk has an upward drift. So it goes up with much higher probability than it goes down, right? So if you set d equals to 3, it goes up with probability 2/3, and it goes down with probability only 1/3. So if I start a little bit away from 0, there is actually a good probability that the walk will just drift upwards into infinity without ever touching 0. Yeah. And it's possible, it's a little bit technical, but possible, but it's fairly standard probability calculations that I'm not going to do. It's possible to show that if you start from k and k is less than n, then the probability that you reach 0 in at most 3 n steps is pretty much the same as the probability of reaching 0 in any number of steps. So let's analyze that instead. So any questions to this cheat? No. And let me remark that this cheat is actually how, or a way of proving the correctness or the running time and the probability analysis for Schoenig's algorithm. You actually prove the inequality that I showed. So that that you can replace at most 3n by eventually losing at most a factor 2 in success probability. Okay, so let's call that pk. Well, now we're going to say that, so what is P1? Well, P1 is the probability of eventually reaching 0 if you start at position 1, right? Now, so P1 is the probability of eventually reaching 0. Well, if I start at 1, I have a probability of 1 over d of just going down, right? Otherwise, I'm going to go up and with probability d minus 1 over d, and then I'm going to be at position 2. And here is the funny thing. The probability of eventually reaching 1 if you start from 2 is, of course, the same as the probability of eventually reaching 0 if you start from 1. Because all you care about is, do I end up 1 below, do I eventually end up 1 below where I am now? So the probability of reaching 0 if the first thing you do is to go up ends up being just P1 squared. Okay, so which means that we get to this equation for P1, and this is, of course, just a quadratic equation in P1, which solves to P1 equals to 1 over d minus 1. Now the question is, why is it 3n and not 4n or 2n? So 3n is, I guess, the lowest number for which the equation, so this equation inequality here holds and is relatively easy to prove.
So,
Yeah,
so Daniel, this thing that you just said, is it fair to say that the transition probability one step doesn't depend on the history of the path? So it's just like where you are now, right? It's like a Markov-like property, right? So the transition.
Yes, exactly. And this is precisely and of course that is true for the SAT algorithm, because whenever we pick up a clause, we always have a probability of at least 1 over d of decreasing distance by 1.
Yeah.
Yeah. Okay. So this is a quadratic equation which solves to P1 equals to 1 over d minus 1. Okay, so here I'm cheating again because it solves to either that or P1 is equal to 1. Yeah, and then you have to go and prove that this P1 equals to 1 solution is nonsense, and I'm not going to do that, but it is nonsense. So there's sort of a true solution and a false solution, and you have to figure out that, well, you don't have probability 1 of returning to 0, of reaching 0 if you start at position 1. Now that you know that P1 is 1, you can analyze what Pk is in the same way as what you analyzed P1. So you say, well, what is the probability of eventually reaching 0 if you start from k? Well, either you go down, yes, with probability 1 over d, and then you have to reach 0 from position k minus 1. So that gives you probability 1 over d times pk minus 1. Or you go up, which means that you do that with probability d minus 1 over d. Yeah, or you go up, and then you, in order to reach 0, since you are at position k plus 1, you first have to reach position k, which happens with probability p1 because you are at position pk plus 1, and then you have to reach 0 again from the same position you started from, which happens with probability pk. Now you see this is actually a linear equation. So if you're doing induction, so you know P1, P2, P3 all the way up to Pk minus 1, then this is a linear equation in Pk, right? Which means that the simple induction shows that Pk is actually 1 over d minus 1 to the power k. So you can just check that you can plug this right-hand side into the equation on the left and make that work. Which of course now means that the probability that a random walk starting from k reaches 0 eventually is 1 over d minus 1 to the power k, which means that the success probability of Schoenig's local search is 1 over d minus 1 to the power k, which means that we need to repeat it d minus 1 to the power k times to get constant success probability, which then in turn means that we get a 2 minus 2 over d to the k algorithm for SAT. Yeah, so what did we just do? We got the d to the k algorithm for permissive local search, which implies a 2 minus 2 over d plus 1 to the n algorithm for dsat, or in general, if you have a d to the k algorithm for permissive local search for any problem, then you get automatically a 2 over d plus 1 to the n algorithm for the problem. And for SAT, we did get some pretty good algorithm, d minus 1 to the k algorithm for permissive local search for dsat, which gave us 2 minus 2 over d to the n algorithm for dsat. Okay, so I have like 5 minutes, right, or 8 minutes to do the second part. Luckily, it's easy enough. I'm going to skip all of the de-randomization and extra stuff that I have at the end, but I can actually cover everything I want to cover about the second part. So what about other problems than that, right? What about vertex cover? What about feedback vertex set, deletion to planar graphs, and so on? Yes? So for example, could we get a 1.5 to the r algorithm for vertex cover local search? And like the best vertex cover algorithm is something like 1.90 to the n. And for a long time, it was something like 1.21 to the power n. So if we could get the 1.5 to the r algorithm for vertex cover local search, then the previous theorem would immediately apply a 1.2 to the n algorithm for vertex cover. So it's very close to the optimum. Yeah. Now, first we should ask ourselves, what does vertex cover local search even mean, right? In this context of these subset problems. It is, so I should give you an input g comma k and ask for a vertex cover of size at most k, but I should also give you some set S of size at most r, and then where I'm asking, does there exist a vertex cover of size at most k, which is at Hamming distance at most r from S. So I have to take S, remove, and flip at most k bits. So either insert or remove at most r elements to get my vertex cover x of size at most k. Okay, and with the parameter being r. This is the important thing, that the parameter is r, the parameter is not k. Okay, and now the question is, well, could we get this sort of fast local search algorithm for vertex cover? If we did, then we would immediately get a fast exact algorithm for vertex cover. Well, the bad news is that this problem is actually doubly one hard. So not only can you not hope for a 1.5 to the r algorithm, you can't hope for 2 to the 2 to the 2 to the 2 to the r kind of algorithm, because like n to the r is close to the best you can do, right? So that's bad. Yeah. Now, what about other problems? Well, unfortunately, this bad news happens for most other problems as well. So for most optimization problems, this sort of local search problem is hard, which means that this approach that we did for SAT is really special to SAT, right? Like while it could have generalized, it just doesn't. So a very natural follow-up is, well, can you make the local search step easier? Can we like put less constraints on the local search problems at the cost of getting a weaker conclusion, right? Like at the cost of not getting quite as good exact algorithms as we would have from a local search algorithm. And this is our main result from 2016 with Fedor Search and Saket. And this is that if you can, instead of just the local search problem, if you can solve the original problem in time c to the k, then you get an algorithm with running time 2 minus 1 over c to the n. And now, two remarks. The first one is that there are some terms and conditions that apply. You will see precisely what terms and conditions they are from the proof. And the second thing is that you should notice that we have a weaker condition, right? We want to, instead of now doing local search parameterized by r, we want to solve the original problem parameterized by k. Notice that local search parameterized by r is a strictly harder problem than finding a solution parameterized by k, because I could give you the initial seed as the empty set. and set R equals K. Yeah, so now like local searching from the empty set is the same as finding a solution of size at most K. Okay, now the second thing is that, well, so because solving the problem is a weaker thing than local searching, we get a weaker conclusion, which means because the thing that we shave off from 2 isn't 2 over C, it is 1 over C. But it is still shaving something off from 2 for every value of C. Okay. An interesting thing is that this theorem has a bunch of corollaries because, of course, we do have a lot of C to the K algorithms for vertex problems, for subset problems. And these magically happen to give algorithms that give the fastest exact algorithms for a number of problems. Some well-studied one is feedback vertex set, which at the time that we published the paper had algorithms with running time 1.73 to the power n, with some really heavy machinery working. We just take the 3 to the k parameterized algorithm, run our theorem through it, and get the 1.666 to the n algorithm. Or for example, for deleting to interval graphs or deleting to proper interval graphs, there was some hard work done to get 1.9999999 to the n algorithm for some fixed number of nines, at most 20 nines, right? And from the parameterized algorithms, we immediately get something like 1.87 to the n and 1.83 to the n. And also because our algorithm works like a black box, just in 2020, feedback vertex set parameterized algorithms got improved from 3 to the k to 2.7 to the k. That immediately implies a better exact algorithm as well. Now the best running time, the running time to beat for feedback vertex set is 1.63 to the n. Okay, so what's the algorithm? The algorithm is a lot like what we did for Schoening. So we assume a C to the k algorithm for the problem, and we want to obtain a 2 minus 1 over C to the n algorithm for in the exact setting. So what do? Well, you have some universe of size n, and you guess what the solution size is. You don't guess the solution, you just guess k. Okay? Then you pick t based on k cleverly. So you pick some parameter t, just like we picked the radius to local search. Then you pick a random subset of size t, and you put it into the solution. So in terms of vertex cover, I would pick a random subset of size t. I say now it is in the vertex cover. Once you say it's in the vertex cover, you just remove it. And the only terms and conditions that apply is that we have to be able to remove S from the instance once we decided that it was in the solution. Because then what are we left with doing? Well, we have to find the solution of size k minus t, yes, in the universe u minus s, where s is the solution that we guessed, or where s is the part of the solution of size t that we guessed. Now, what is the running time for this? Well, we're now looking for a solution of size k minus t, because we had a solution of size k, we guessed the subset of size t, and we got rid of it. So the running time will be c to the k minus t. So what is the analysis for this? Well, the running time is always c to the power k minus t. Yeah. It has no false positives. If you find a solution, well, it's a solution. And now the question is, what's the probability of finding the solution if there is one? Well, again, we have a fraction, yes, where the number of the good ways is picking is as long as we are picking a set of size t, which is actually a subset of the solution of size s of k, right? So suppose there was a solution of size k, the probability that we pick a subset of it is just k choose t, right? Now, how many ways are there to pick a subset of size t total? Well, it's n choose t. So the probability is the number of ways to pick a subset of size t from the solution, divided by the number of ways to pick a subset of size t at all. Okay, so what does the running time? Well, we need to, in order to get constant success probability, we need to repeat it this many times, right? N choose t over k choose t times. So the total running time ends up being n choose t divided by k choose t times the running time of the algorithm, c to the k minus t. Now, where does t come from? Well, we pick t. We are the ones who are free to pick t, and we pick t so that this expression gets minimized. But then, what is k? Well, k is whatever the worst solution size is for that n, yes, that will maximize this expression. So the total running time is this min-max expression. Notice over something that doesn't depend over the instance at all, right? So this is just something that depends on n, yeah, or n and the constant c. And with a little bit of calculus, you can actually calculate and prove that this is at most 2 minus 1 over c to the n. So that is actually the entire proof for our main theorem, other than this simplification and analysis for the running time. Now, let me, before I finish, state the analysis, state the main theorem a little bit more properly without the terms and conditions. And the terms and conditions is that now, if I give you a set S that I promise to be a subset of the solution, and I give you a set of size t, which is a subset of the solution, and I ask you, can I extend this set of size t to a solution of size k in time c to the k minus t, right? So if I can do this, then I can solve the problem in time 2 minus 1 over c to the n. Yeah. And this monotone local search problem for most subset problems, like the moment I decide that some elements are in the solution, I can just remove them. And that will just reduce to solving the original subset problem in c to the k time. Yep. So this can be de-randomized, but let me show you some open problems. So the first thing is, it's not clear how to improve it at all, right? So it would be nice to beat the running times that we get, and in particular to try to combine parameterized algorithms with the well-known techniques in exact algorithms, like measure and conquer, in some meaningful ways. So there has been a little bit of work done by Serge Gaspers after this, but still not much. And I think there's like a wealth of exact algorithms that can be improved if you just find the right way of combining this technique with measure and conquer. And one problem where this extension, where the extension problem doesn't quite work out is dominating set. So the question is there some way of making this technique work to get a fast exact algorithm for dominating set? Yeah. Thanks.
Okay, thank you so much for the talk.